Let's go. All right. So what happens when our cells are not at standard conditions? Okay. So let's back up for just 1 minute and I'll remind you where the hell is that stuff? Standard states, 1 molar. Okay. What if we're not at 1 molar, which is pretty much all the time, right? It's very difficult to arrange these electrochemical cells to be exactly 1.00 molar. So we have to have a way of adjusting our calculations when we're not at 1 molar, which is most of the time. Okay? And so to do that, we're going to rely on an equation we introduced in thermodynamics. And so I'll just remind you, right, from chapter 17. Okay? So our total delta G equals our standard delta G plus RT natural log of Q. Okay? Reaction quotient, right? And so, and I'll remind you, this is for non-equilibrium. When we're at equilibrium, this equation becomes 0 equals standard delta G plus RT natural log of K. All right. And most of the time when we use this problem, we're going to be using this version because we're not going to be at equilibrium. And in fact, as we'll see, I'll foreshadow a little bit, when our battery reaches equilibrium, it's no longer working. It has to be recharged, okay? So typically batteries are in non-equilibrium conditions. So now if I expand this equation, I know I can write delta G as negative NF E cell. I can write standard delta G as negative NF E cell standard plus RTLNQ. And doing some algebra, right? So this is dividing the whole equation by negative NF. Okay, so you can see that was done here. And so now what we get is our observed cell potential. So I'll write non-standard. So in other words, the cell potential if it's not 1 molar. And that equals the standard cell potential if it is 1 molar, our standard value, minus the constants R times temperature divided by N, number of moles of electrons, right? Faraday's constant and natural log of Q. Okay, and this is known famously as the Nernst equation. Okay, and I want you to recognize that by name, the Nernst equation. So you notice here I've got two versions of this written, and typically what is done if we're at, oops, let me undo that. If we are at 298K and we collect all of these constants, right? R is a constant, T is a constant, and F is a constant, and N is a constant, but it can change depending on what our electrochemical cell is, right? And then historically, the log is used, so that's log base 10. So I'll write base 10. So really, this is kind of like a historical version of this equation. So right, keeping track, that's different. Right down here, it's natural log. Up here, that's log base 10. Let me write that 10 better, okay? Then we can use this version directly. If we're at 298K, all of those constants become 0.0592 volts divided by the number of moles of electrons and our standard cell potential. And of course, we could still use this whole full formula if we wanted to, if we weren't at 298K. So that's really the only reason we would use this one. So I'll say use this one if not at 298K. Use this one if we know that it's at 298K. Okay, so let's do a sample problem, and I'm going to record that in a second part because this is part B, because this is a fairly large example to go through. So I'll see you in the part B video.